first time he hasn't had a car parked in the driveway, so he can go to
True.
the shop.
It's true. Good point.
Do you know what? Do you want to get Dave walking up to the front door?
Well, I was thinking about that. Good, Dave, go walk up to the front door, would you please?
Yeah, sure. Slowly.
From over here. Going this way. Yep. Okay.
As we were discussing, Dave, looking at pretty well established now acceleration of the expansion of the universe, which requires some kind of anti-gravitational force, and the additional dark matter problem where there has to be an additional force holding the galaxies themselves together, the matter. And the conventional approach is to look for normal matter inside, pulling the mass back together.
Sure.
We're going to try to think about something outside repelling the matter towards the inside, and see if we can't come up with a standard mechanism for both forces, sets of forces.
Sure, sure, sure.
So first thing we have to talk about is the fact that we really don't have force fields in the vacuum. It's fairly well known, particularly in Feynman's 3 volumes. He'll explain it very well, that in the vacuum you don't yet have force. You merely have a change in the space-time itself, if you like relativity view, or we have a change in the virtual particle flux of the vacuum if we choose to use the particle view. Either way we have is a change in space and space-time.
Precursor field, yeah.
And so we have, on one hand, we have a curvature of space-time, which puts us in the business of gravity. And at the same time, we have a change in the actual density and intensity of the virtual particle flux of vacuum, which puts us right into particle physics. So if we take that view that we're really talking about the same thing when we talk about either one of those views, we have to, for the key to it, we have to go all the way back to Dirac's electron theory, where he conceived of the Dirac sea.
Sure.
And as you well know, he modeled the vacuum with little holes in it, negative energy holes, exactly the size or absence of mass energy of one electron. So it's a negative energy type electron rather than a full-bore positron.
Sure.
And
it's important to make that distinction, isn't it? Because it's, you know, like we were saying the other day, that you can have pair creation and annihilation, but of course if the masses of the two pairs that are annihilating, you know, say both positive mass, you know, you're going to get a photon energy of 2m, or the, you know, the sum of the masses.
that's correct.
Whereas if you have a hole,
This is beyond the photon, the pair annihilation and pair creation.
sure.
Because if I have pair creation, and if this is a zero level of the vacuum, when all the holes are filled with electrons, the Dirac sea is a field Dirac sea,
Sure.
and it's all filled up. I have a positron and I have an electron. The energy is all above the zero. It's all positive, positive energy, positive mass. And that's quite different from a hole, for example, the positron. It has positive energy, positive mass, and of course there's a source charge, so it produces fields and potentials with positive energy in them. That's quite different from a hole, an actual hole where the electron has been lifted by adding some energy to it and popping it out of there and leaving the hole. The hole itself is below the zero level, so we cannot say this is a positron. That's positive energy because the energy is negative. We can't say it's positive mass energy because the mass energy is negative. So there is a difference between the hole and the positron, and it's not involved, that difference does not appear in pair annihilation or pair creation in the equations and all for that. But if we take this hole and we say, okay, what is this hole? And how does it operate? It is a charge.
Sure.
But it's negative energy, negative mass charge. So, and that's interesting because if I treat it as a source charge, it also will produce EM fields and EM potentials spreading at the speed of light, you know, from the time of creation of the thing in all directions. Real photons in them, but now these photons have negative energy. They came from below the zero of the vacuum. And so I now am surrounded with negative energy EM fields and negative energy EM potentials. Now, if the hole interacts with matter, it's going to eat another electron. And by the way, that is not pair annihilation. There's no radiation.
Sure.
Instead of two things here, both with plus energy, interacting and creating a photon that's above that, you know, photons with positive energy. Everything stayed positive energy. This one, I have negative energy interacting positively. Just go to zero. That's all, just a field hole. There's no radiation.
Yeah.
So if we look at the hole and we say, we connect with one more fact out of all things, thermodynamics particularly. Whenever we have a very sharp gradient across a certain area of the vacuum or space-time, we produce a very sharp space-time curvature, which is lots of energy density, and at the same time it's known to violate standard thermodynamics. They formed another kind of thermodynamics to even try to study it. And the thermodynamicists say not much is known about this, either theoretically or experimentally yet. But we know it's there, we validate it's there. Prigogine on page, and Condiputi on page 459 of their Modern Thermodynamics spell out some areas that are known to violate thermodynamics. And this is one of them. Well, what really happens in this gradient, energy density look at, we pop out some electrons and we leave some holes. Well, the electron and the hole repel each other.
Sure, sure.
So the hole takes off in one direction, the electron takes off in the other. So if you look at a circuit that you use very sharp spikes in, across little pieces of space-time, particularly over towards the output section, you will find that you do pop out some extra electrons, and they just look as regular current. They'll try to go from the input to the output to ground and back. But the holes go exactly the opposite way. They head from output back to the input, and they love to go against the back EMF.
And try to destroy the...
So we ran into, experimentally, the fact that there was something mysterious coming out of our output section, which would appear back in our input section and start to eat electrons without any radiation. We were not emitting gamma radiation. We didn't get radiation sickness. But we would have to put in more power, that is more current, from the source in order to have enough left over after we filled the holes that kept appearing to power the circuit. And it's sort of nature's way to decay an over-unity system, COP over unity, where you're producing partly negative energy and partly positive, and if you're not careful, the negative energy will come fix it to where it looks like a load sitting in your input section.
Sure.
And your output, or your external power system, then has to put in more power because it's got a power filling the holes plus power operating the circuit.
I suppose it's important to point out when you say gamma rays, you know, the photons you get off of pair creation could be the wavelength equal to the energy of the two masses, I suppose. Is it true to say that that gamma rays are the only wavelength you're getting off? Or?
No, not necessarily. As you know, the direct electron approach has been at least considered.
Sure.
That you could build a C also that has a proton hole in it and protons and all, but you'd have to add quite a bit of energy, very sharp gradients to lift out any protons. It's much easier to lift out electrons from the vacuum than other. But in theory, you can extend it to any other kind of particle if you have enough energy and enough gradient to deal with. But the beautiful thing is that once we have the holes persisting for a while, some short period of time in a circuit, and their fields of negative energy are traveling at the speed of light.
Sure.
So just a slight persistence gives me the field energy flowing. That's a pointing energy flow, but of negative energy. And so I get an extra pointing energy flow which goes backwards in the circuit. That's what got us so confused when we ran into it, was it goes backwards.
Yeah.
It goes against the forward EMF rather than with the forward EMF. So that's what it turned out to be after lots of struggle with it. The Sweet device, for example, almost all its output energy was negative energy. You could short the leads of the operating system when it's putting out 500 watts. You could suddenly short the two output leads together. You would not have the typical flash and you know, melting of the copper and all that at all. For a short circuit, what you would have is instant freezing of water, ice on the thing from the water vapor in the air, just instantly coated with ice. And if you've stumbled onto a shock of it in your body, it would sort of freeze some of the nerves a little, and it took a while to heal. So we did have negative energy, and that was very interesting to be able to work with that a little bit, you know, through Sweet, because it was Sweet's invention.
Sure.
And we did suggest since negative energy with the fields, if there's enough of it, is there enough extra stuff riding with it that's negative energy, you could do anti-gravity with it because it repels normal positive energy matter. Protons and neutrons and things like that, and normal electrons and normal matter, it's repelled. It repels those and is repelled by them. So the thing to do was to put that to the test and see if it really does produce anti-gravity. His unit had such a COP, gain, you might say. It was 1,500,000 at 500 watts, and you could push it. So it looked like we had to increase the gain. There was a slight change in weight on the bench as measured fairly accurately at 500 watts. But it looks like we were starting on an exponential curve like this. So I convinced Sweet to do an anti-gravity experiment, push it, to double the output. And he built an extra output section to do this and connected it up. Sadly, I was not able to get there for the actual experiment, but I was on the phone here in Huntsville as he was doing the experiment, reading the results to me on the phone, and I was recording. And it plotted the prettiest curve you've ever seen. Nice. It lost 90% of the weight on the bench very smoothly as you increase the load, and did show very clearly the anti-gravity effect, which we were then able to explain. We even got a minor publication of the results of that test. But, you know, the unfortunate loss of the Sweet device and so forth. So we were not ultimately able to pursue that, although it was one of those things that was bitterly disappointing because, you know, we really wanted to go to the scientific community, get it really validated, get some really high-powered scientists on it and looking at it and so forth. We were never able to do that. Sure. But it did prove the fact that you can have negative energy in a circuit, and it does produce it will power resistors. You've got to watch how you wire things up and that sort of thing. You can also turn it back into negative energy, a positive energy. You simply take a capacitor, flip the, and charge it as if it were charging it backwards for some strange reason, and it'll charge up normally. And then you turn it back the right way, and it'll discharge normal positive energy. Sure, sure. So it is very useful if you can do it, because it has another great advantage discovered by Beardenem, that if you have an impedance, if you go down a wire conductor, let's do some meaning of what we really mean functionally when we say certain words. When I say conductivity of a conductor, what I really mean is that the conductor acts as a sort of inverse waveguide, and it holds the energy flowing along. If it's a perfect conductor, if I put in positive energy on this end, on the other end of this conductive section, I'll get exactly out the same energy flow I put in, won't lose any of it. So now if I have an impedance section in here, by definition, that's a reduction in conductivity, which is a reduction in the ability to hold that energy. Positive energy is always trying to escape. It's divergent. It always tries to diverge. Conductivity is the ability to hold it and prevent it from diverging from the line of propagation. So if I have a impedance section, what I have said is I've reduced the ability to hold that energy, and some of it will diverge and escape, and that's called losses in the circuit. Sure. And on the other side of this impedance, if I carefully measure, I will have less energy coming out than what I have put in on the other side. But if I will measure, if it's a resistor, for example, I measure the heat, I will have the additional energy have been radiated back to the environment, but lost to the circuit, lost to me, to my ability to use it to go power some more loads. That's not what happens with negative energy. Remember, it goes backwards. It's converging. Negative energy is always excess negative energy. To any negative energy flowing down a wire, the environment is trying to pour in excess negative energy all the time. You're having to fight it off. And conductivity is the ability to hold it back and not let it pour in. If I meet an impedance section, just a normal resistor, a normal capacitor, a normal inductor, the fact that it has impedance says it has reduced the conductivity. Now in our terms and what we're interested in, it has reduced the ability of that wire circuit at that point to prevent extra energy from coming in. So extra energy now will bleed in, negative energy. And on the other side, if I carefully measure everything, by the way, to measure it, you have to catch it and convert it back to positive, and then your instruments will measure it. Sure. Same thing for the input. So you can measure it if you always remember you have to measure what it changes into when you make it into positive energy. Convert it there for the measurement. but I will have more negative energy going out of the impedance section than I myself put in, freely added by the environment. Any environment, anywhere, the vacuum itself adds it. Curved space-time adds it. So at that point, I'm in business, because if I put in a little energy, negative energy, with a process that's doing my, I'm taking the advice of the thermodynamicists, and I'm making a sharp gradient, and I'm lifting these electrons out and getting them out of the way, and then I'm using these holes momentarily and the fields from them. As this pointing negative energy flows down there, now I have built-in amplifiers by just sticking impedance, stick some resistors in series.
Sure.
Works backwards from a normal circuit. This is not in your textbook. So what happens is, every place I put another one, I get more out on the other side than entered the front end of it. It becomes like an amplifier. It has gain. But it's real energy gain, and you're not violating conservation of energy because the environment's putting it in. It's like a heat pump. Only now it's a cold pump, so to speak. And what's happening is the environment's putting in the extra negative energy. But if you build up a lot of negative energy and then you simply charge something like a big battery, big bank of batteries, big bank of capacitors, and switch them around the other way normally and discharge them, you get normal energy. You can turn it back into energy to run motors and normal systems that we build. One day we will also build the load, which has impedance also. If it's not a purely resistive load, we will probably build the load to use that gain. And maybe the load increases the gain further by a factor of 10. Or excess energy is coming into the load directly from the environment. But we'll have to redesign our motors and generators in order to do that. But one day we will probably design motors and other loads. A lot of them will be designed to use that effect. That's maybe a gain of 10 right at the end when you just feed the motor. But we're talking about an area which theoretically we're going to be able to put in a little energy by just fairly simple circuit arrangements to take out lots of energy that the vacuum very graciously gave us for free. All we had to do was ask for it, right? And then we can use that to power our loads. And we can greatly reduce the emissions and things like that in the biosphere. Now, the higher the COP of a unit over unity system, it appears the more percentage of the output energy gets converted into negative energy in the output. So the more likely it is, unless you're very careful, to set up its own feedback loop, eat more current coming in from your external generator, and defeat the whole system, turn back into an under unity system. So one of the things we have to get across to every experimenter is the fact that don't allow negative energy to defeat you by the input section load effect. Catch it in the input section like Beardenem knows how to do and does. Turn it back into negative, positive energy and use it to help you power your regular system that you're trying to operate. We go through all of that because now let's move to astronomy, where we're interested in dark energy and dark matter. And we've got to get it to gravitational. We need one more fact before we can get at the gravitational effect with a sufficient amount of it. The business of energy flow through space did not exist in Maxwell's time. By the time Maxwell died in 1879, that concept had not been born. It was created in the 1880s by two men, independently and at the same time, Oliver Heaviside and Poynting. Now, Poynting was an academician, and he published very prestigiously in the Proceedings of the Royal Society. But Poynting only considered the divergent energy. He only considered the energy that enters the circuit from outside. And by definition, that's, diverges into it from the flow we produce out of a normal generator or something. Sure. So he only considered positive energy, and he only considered the part that will diverge. The divergence of this energy flow is not zero. It has to be a positive amount. Heaviside discovered that. He also discovered the direction of the general flow of the energy is along the wire, not perpendicular to it like Poynting thought. And he did correct Poynting on the direction in a Royal Society publication. But Heaviside discovered something else very startling. He discovered that the divergence component was very small, tiny. Most of the component did not diverge, of the flow didn't diverge at all. And it's about 1 trillion times of it in an average little circuit. As much that doesn't diverge as there is that diverges. Well, this is interesting because if this is true, this means that from every generator and every battery that we build, not only does there outpour the divergent energy that we measure in our circuits and all, but there is about 1 trillion times as much energy coming out of that that never diverges in anything outside, and never does any effect. Well, in those days, in the 1880s and 1890s, particularly by the 90s, when people are beginning to look at this and try to figure out where on earth can we possibly explain this huge component of energy, that's, if it's 1 trillion times as much as the energy we're cranking the shaft of the generator, we got a problem, because we haven't got the foggiest notion where it could be coming from. They had no active vacuum. Most of particle physics still wasn't born. In fact, along about that time, they were trying to discover the electron. They still were dealing with the material ether. It was only 1887 before that got destroyed, and it took another 10, 15 years before they really got serious about it. So they were struggling with lots of things that were in the way of really understanding it.
When you said before about the divergence, I mean, when you consider divergence, are you talking about, I mean, the heaviside component?
The heaviside component, that's a good point. It's a totally swirling or curl component. So totally, you got to express it as a curl.
Sure.
And just looking at it in vector analysis, the divergence of the curl is equal to 0. And of course, we have assumed in this model flat space-time, no curvature. But unless you have appreciable curvature, the divergence is so near 0 you won't even measure it with your instruments, or maybe the teeniest bit you couldn't separate from noise. It would be so small that you couldn't even worry about it, account for it. If you achieve, theoretically now, if you achieve sufficient curvature of space-time, the divergence will not be 0, and you will have parts of it appearing, real energy entering the circuit of the process that you're using and showing up as real, emitted energy. A place where that happens is in an area called negative resonance absorption of the medium. It's a fairly narrow little area of optical physics, but it's a good area and very, very nicely done. It's been there since 1967 or so. Ledakov, Boring, people like that work in it all the time. And what we call the field is defined for a static charge, a reaction to what the real field is, which is force-free, interacting with the source charge and producing a force in static charged matter. They assume the charge is static. And what we call an E field in electrodynamics is really that interaction, results of it, the effect of that interaction. The force appears only in matter, does never appear in space. So, but if the same charge is not static, but I'm feeding energy at a certain frequency into it, and this thing happens to be on little, it can either be on conducting media or it can be on dielectric media.
Sure.
The dielectric goes good for one end, you take the IR and the UV. Dielectric will go, I believe, on the IR end. I believe it's the conductor that's on that will give you the ultraviolet end. So you want to, depending on which way you wire the thing, you want to use ultraviolet or infrared. Infrared is heat, so all of a sudden we tie into thermodynamics real well. But if you have this thing self-resonant, particle is sized so that particle resonance occurs at exactly the frequency it's being fed, then if I feed IR energy into it, it will go into self-resonance and sweep out a much larger reaction cross-section. It will in fact diverge more energy, and there specifically about 18 times in the average experiment. The medium that's made of these self-resonant particles will therefore receive, we think all we put in was a pointing component, which is all we calculate. It will think that's all it received, and it will output 18 times as much pointing, having diverged energy. So it's a mystery because to stay away from the thermodynamics of it, people just talk about the reaction cross-section increasing. We know now, however, that we really did put in a lot more energy in terms of the heaviside component. If we go back and pick up that component, we put in a lot more than we accounted for, and it tapped just a little tiny bit of that heaviside component. The way the heaviside component got thrown out is Lorentz took a look at that in the 1890s. He was the most famous scientist alive in electrodynamics, particularly at that time, electrophysics. And Lorentz said, well, it doesn't do anything. Like everybody else, he didn't have a source of it. There wasn't any active vacuum or anything for him. Relativity hadn't been born yet for curved space-time. So he said, well, it doesn't do anything, doesn't interact with anything, so it can have no physical significance. This was the terms that he used. So he originated the little trick of assuming a closed surface around any volume element and integrating the entire energy flow vector, which is now both the pointing and the heaviside components, around the entire closed surface with surface integration. When you do that, you eliminate any component that goes straight through. It's positive going in, negative going out, and you throw it away.
So I guess you could say that this was kind of like the final distillation process of melting down Maxwell's original information.
That's correct.
And yeah, ending up with the theory which we have today.
They didn't really discard the physical flow in nature.
Mm-hmm.
What they discarded, really, being very precise, was any further accounting of it because, as he said, it doesn't have any physical significance, so why bother? So now we have a situation where, for the heaviside component, once we use this little integration trick, which Lorentz taught us to do, and once we have in our head the idea that you're never going to get any physical significance from this flow, even if it were there,
Sure.
it means that no one investigated it any further. It means it just got wiped out of the books and walked aside and left. It's still there.
I suppose in a way you could say this is a little bit similar to the idea of what we have with, say, the 0 point energy, the virtual state energy. You know, you're not seeing any physical significance directly. You know, experimentation you can do is limited only to what you've done.
That's right.
So if you don't have anything that's going to show that up, I suppose in Lorentz in the same way was sort of justified in doing that. I mean, that at that time they're only looking at systems they could use and power loads and so forth.
Well, ultimately, the science has to be justified by an experimental result.
Sure.
And if the thing won't have any action for you, it won't give you an experimental result, and they didn't find any at that time that did, then the statement was correct. It really would have no physical significance, and you may as well ignore it.
So,
however, gravitational, you see, we hadn't had relativity born yet.
Sure, yeah.
But the energy being there is a change in the energy density of space, and an appreciable change, since it's a billion times, a trillion times what we would normally account. So we have a tremendous change in gravitational ability. We can no longer sweep the little change of gravity due to just a little bit of electromagnetic energy. Now we have same coupling constant with a lot more energy. So now it can have an appreciable gravitational effect. That's the whole point. And the other whole point is that with negative energy, it'll have anti-gravity effects. And when I consider not just the pointing component, but the heaviside component, this extraordinarily large component of negative energy flow now suddenly gives me appreciable anti-gravity effect.
Sure.
So now we're suddenly, with a light bulb lit in our head, seeing, you mean if we could evoke quite a bit of this in a circuit, we could actually produce practical anti-gravity.
So this could apply to spatial expansion, like the acceleration of the universe and so forth.
That's correct, absolutely. So what we're looking at with astronomy, we're looking at gravitational effects in the large, out here in the galaxy and out between galaxies and universe. Now what we find looking between the galaxies, looking at all the galaxies in the universe, we find a very strange thing. We always knew that they were expanding, but we thought positive gravity was gradually slowing it down.
Yeah, sure.
Well, some years ago, some measurements suggested that wasn't what's happening, but in fact, it was doing the other thing, it was speeding up. Well, this means that all the positive energy between these galaxies is still trying to attract and slow it down. Something is overcoming that attraction and adding further acceleration. That's got to be anti-gravity.
Exactly, yeah.
So we're now looking for a source of anti-gravity out between the galaxies, which is repelling, therefore would repel the matter in all the galaxies. All matter would be expanding, and so it would be accelerating.
Sure.
That's, of course, dark energy. They considered some kind of strange energy, which is like 70% of the energy in the universe, it turns out, something like that, 2/3 something, that we haven't seen. We don't know what it is, but we see the results of it acting. And today, there's no longer any question, to anybody reasonable at all. There's several different things now which establish the acceleration, that we pretty well know now the universe is accelerating its expansion. So now we know we've got something very strange out there making an anti-gravitational force, and we haven't got anything in our theory that comes up with it. We're theorizing all kind of exotic stuff and all this. And I think the answer is to go back and pick up that little hole that everybody walked off and left, that it really exists in direct theory. It is a source charge. It does produce anti-gravity. If I add the heaviside component to the normal pointing flow, I suddenly have something that can produce significant anti-gravity. And I have another remarkable thing. if I take in galactic processes where I have many, many sharp gradients, terrible gradients, and very explosive actions and so forth. I mean, everything from gamma ray bursters.
So what you mean by sharp gradient is a huge difference in energy?
A very quick change of, and very sharp change of energy density in space. We're going to lift lots of electrons and maybe even a few protons and things like that out of this Dirac sea, maybe the expanded Dirac sea if I include protons. But let's just stay with electrons for simplicity.
Sure.
But suppose we just stayed with electrons. I'm going to lift a lot of electrons out of here because I added energy to do that. But I left the holes.
Sure.
They haven't filled yet. Well, then the electrons are not going to fall back in the holes because the electrons are going to go this way and the holes are going to go to the other. They repel each other. So now I have a funny thing. I have the holes also are repelled by all the masses around them. Well, usually the galaxy is not entirely symmetrical everywhere. So anywhere there's a little change and it's asymmetrical, that hole's going to accelerate, be accelerated by repulsion through that place there. So the galaxy is going to be like a whole bunch of little guns firing out all these holes, flows of holes, and their fields are going like crazy as long as those holes exist. They're producing and adding energy to the vacuum all the time, negative energy. Well, what we will have is we will flow outside the galaxy and we will start filling in space between all the galaxies with excess holes. And the holes are repelled by the galactic matter. Once they get outside, they're repelled further away, but they're also repelling at a distance any other galaxy. So we have a very strange situation where they will be retarded a bit, so they'll start to pile up. The further you get out, somewhere between galaxies, you start to get a pile like this. And so between two galaxies here, with a pile of negative energy charges in the middle here, with their fields and all continuously pouring out, I am continually repelling the matter in this galaxy, and I am continually repelling here, and so we're expanding the galaxy, increasing and accelerating the expansion of the galaxy. So that takes care of a real rough approach to what cold energy might be, dark energy might be. And of course, it's got to be followed up with experiment and theory and that sort of thing. But now let's take the same thing and let's get the dark matter effect.
Sure. So that's the idea of galaxies not having enough matter to gravitationally keep themselves stable in the system.
That's correct. It has been well documented now. It's established, clearly in astrophysics and astronomy that the galaxies, particularly like spiral galaxies, there is not enough gravitational pull to hold all due to the acceleration trying to, the masses trying to fly apart. There's not really enough of normal gravitational pull to hold the thing together. It should fly apart, and it doesn't. So the point is there's something extra holding it in. Now, we have assumed that it had to be, since it's got to be gravitational, we always like to think positive energy. We never think of negative energy unless we confronted with it direct like we were between galaxies and generated the dark energy. But for the dark matter, they're trying to conceive of some peculiar kind of matter that doesn't interact with photons, but it's normal energy and normal matter, except for that. Because we can run all the photon observations through there we wish to, we see no interaction with normal matter. So it's got to be dark matter. That means photon non-interactive, which means very exotic, something we don't see in the laboratory and haven't seen at all. But let's get a little bit more fundamental. What we really are saying is, let's take each piece of mass in this galaxy or in one spiral arm. There has to be a set of forces directed within on all this matter. There has to be forces directed in to be pushing it in, compressing. In other words, instead of pulling it in from the outside, there really is a force directed. We don't care what generated it, whether it's inside or outside, as long as the forces are there and they're going in the right direction. So let's go to the forces and forget whether we have matter or what. Let's see what will generate the forces. Hey, our pilot is
holes outside.
From every side of that galaxy in every direction, they poured out all these holes, and they're pushing back on the galaxy in every direction from outside. So we have our compressive forces, which far too little if we only consider the normal electromagnetics and the normal pointing component. But if we consider this much greater heaviside component, now we're in business. Now we suddenly have it's not insignificant. The effect is now definitely there. So now we have enough to repel the arms of the galaxies back. And it's stronger because these things are much closer in distance to the galaxy than they are to a distant galaxy way off down there. We'll have a much stronger effect pushing it back in together, and that holds them together. And because with the dark matter approach, we could only find about 4% of the matter of the universe. The rest of it's dark.
Exactly.
And we haven't found it with our telescopes. We haven't found it in the laboratory or anything. Now we can at least do some pulsing experiments in the lab where we can produce the holes, and over a period of time we can design and generate experiments and maybe change some instrumentation to where we can now start to make an observational science of it. And then we can get numbers and we can start to look at what size this is, what density this is, and so forth. There's a whole science here waiting to be born with a new kind of energy, negative energy, which you can do in the laboratory. If you know that when you pulse very sharp gradients, that you can lift the electrons out and have the holes left and persist for a while, then you can play with the negative energy flows that come from that in the negative energy fields and potentials. But there's one other effect that even adds to it. NASA fired launched way back, you know, in the 90s and all, a couple of spacecraft, Pioneers, 10 and 11. And there was another one, Ulysses, that also showed the effect. There's a strange thing happening with these probes, these space probes. Here's the sun here, and they're outside, departing away from the sun. They've been there for years, moving way out. But they're moving slower than they should be moving by the total conventional theory we have. Something is retarding their leaving the sun.
So in essence, you've got the same situation with the galaxies in between, say, the sun and the Earth.
Between the sun and any other part of the galaxy, a star, between it and any other star, it's got all kind of explosive and sharp gradient processes going on there. It's boiling out holes, and they're piling up around the sun and reaching on out past the galaxy and everything else. But there's a pile up in there where your probes are flying, and they're flying towards the pile up in the middle. They're getting excess forces pushing back on them for retardation. So we would predict if this other is, you know, is fitted and shown and observed, and enough in a lab is done to show that, we would predict that those spaceships would in fact have a retarding force exerted on them, and therefore they wouldn't be as far out as they should have been by our normal predictions. And they are not.
I suppose it's worth pointing out that the sort of Newtonian mechanics, which say NASA uses to regularly calculate orbits and so forth, directly raise just a positive energy and just a positive mass.
That's
not
correct.
Dealing with negative energy at all.
That's right. They didn't take any kind of negative energy into account. As far as I know, the first time they started accounting that was either when they got to black holes, they tried it a little, and then when they got into the necessity for dark energy, they didn't know what else to try. They had to have anti-gravity. So they started saying, well, the only thing out there's not a lot of mass out there, so there's got to be a lot of energy, and it's got to be dark energy because it's got to generate anti-gravity, not normal gravity. So we think that we have something here which can be shown experimentally first. We can produce the Dirac holes persisting for a while in our circuits. And, you know, they only have to persist for a little bit because they're radiating at the speed of light, negative energy photons. So the fields and potentials are negative energy fields and potentials. And we can actually do experiments with negative energy in the lab. We can also, by producing significant gradients and things like that, we do change the curvature of space-time very sharply, and we can involve that heaviside component doing that sharp gradient. That's the reason we got enough energy to affect this stuff in the first place. So we can do all of the things. It's still crude, it's still got to be refined, it's got to be made into a science and the experiments done and all, but we have a clear conceptual route by which we can go after the effects from what we are now calling dark matter and dark energy, and we can produce the dark energy in the laboratory. And we can, in fact, use it to power circuits and give us gain in it.
Tom, a quick question. What, in the foregoing discussion, has consideration been given to the term and usage of antimatter?
Antimatter is a little bit different, isn't it?
Antimatter normally...
It's not the same as dark matter.
No. When a physicist says antimatter, what he normally means is for every particle of positive energy, I have another particle of positive energy, but with opposite charge, if I'm talking with charges.
And spin as well.
And spin as well. So if I say an electron with energy, you know, positive energy up above the zero of the vacuum, zero level, the assumed zero level, then I'm saying a positron, which is also up above there. So I've got positive energy in both.
Sure.
Now, if I meet these two and these two meet each other and annihilate, the energy has to be conserved, and it's all positive energy. So I get the total energy that was in both of those and their kinetic energy. I get photons born with all that energy in it. If I do pair creation, I have a change in photon energy that's all up above the vacuum, zero, and the energy sort of breaks, you know, the photons are really changing into particles and all with the Feynman dance. It's not a solid photon all the time. It's not a solid electron all the time like a little ball. That's not what happens in nature. The thing is undergoing all kinds of interactions. It changes into photons, and they break into positron and electrons, and they recombine. They do all kinds of crazy dance. It's called the Feynman dance, and physicists are very familiar with it. So what happens is, in the Feynman dance, when this thing breaks into a positron and an electron, it has to be that because it's positive energy. There's no negative energy for it to have. So it's going to be a positron and an electron, and if it's in a sharp enough curvature, these break apart. And that's pair creation. When they do exactly the opposite, they come back together and eliminate one another and turn into photon, we get suddenly a burst of photon with all that energy in it, and that's pair annihilation. But it was all positive energy. There was no negative energy in here anywhere, and we did not involve a hole. So the hole has negative energy, you see. So the problem has been that every time we say a Dirac hole, we have been taught to immediately switch our minds and replace it with a positron. We go from the negative energy below here, we just jump without any input or anything. We just assume the positron, and that's false. That's not true. And so when the physicist says antimatter, he's staying up here. He's not playing down here underneath the vacuum zero. But what we're looking at with the anti-gravity and the dark energy and the dark matter effects, the forces on the matter, they're being produced by the stuff that's underneath the vacuum zero. So we have to actually go after the negative energy and negative mass holes and start to use them to get at what really the dark energy and the dark matter is.
So it's also worth pointing out that also that because with antimatter the mass is still positive, mass is like in the electrical sense, like electrical charge gives off fields, you know, electromagnetic and so forth. You know, masses give off gravitational fields, so the mass is kind of considered as, or gravitational mass is considered as a gravitational charge. So because they're both positive, they're both you know, positive gravity effects and not anti-gravity effects. Whereas in the whole case, because of negative mass, so negative charge gives off an anti-gravity effect.
And we get enough to have something practical. If we wanted to go after, let's build some anti-gravity things, you know, lifters, ships, whatever, get some effects at least in the laboratory. We have enough of it if we include the heaviside component to be able to do that. So if we can produce enough of the holes around for a long enough time, and we have that heaviside component being negative energy now, we can produce enough enough anti-gravity in the lab to be able to see it. And that's what the Sweet experiment was doing.
And Sweet actually was able to fly his thing around the room, wasn't he?
Well, Sweet told me later we were being very cautious because when you push these magnets that he had, they were specially activated. If you pushed them too far, they would explode like hand grenades, like a fragmentation grenade. Talking to Sweet later, I had urged him above whatever he did, above all else, do not go past 1,000 watt output, because we were risking explosion of the magnets if he did, and I didn't want to see him get hurt or killed. It was doing this in a bedroom, for goodness sake, with benches, you know, and this equipment on it. So, and he did explode, by the way, a few magnets from time to time. But there was no need risking his life because 90% loss of the weight is certainly a good demonstration, and it's beyond any kind of noise effect or instrumental measurement effect you could possibly do. So it's certainly good enough. But he told me that his curiosity got the best of him. He just flat couldn't contain it, and that he finally took the unit and decided to push it further, built him some more output unit to put on it so he could push it on up and load. And then what he did is he tied the thing to a tether tied to the bedpost. And so then he powered it up, and at this time it went on up and levitated up on the end of the tether. So he said, I put a string on the front so that I could pull the front down and can it so I could get a propulsion force. And he said he flew the thing round and around on the string around his bedpost on this tether. But he said he did it because, and he risked it because he just couldn't contain himself. He had to do it. And of course, you know the rest of the story. Not very long thereafter, there was an attempt on his life. Sniper from about 200 yards with a silenced rifle. The only way it missed him was he stumbled and fell just as the bullet went by his head. And it frightened him so bad, he started getting threats all night. They'd call on the phone. They were threatening his family. They'd follow him around in the shopping center. And he was threatened so much and it scared him so bad that he buried the experiment, never talked to it again, would never do it again, would never talk to his investors about it, and just hushed it up because he felt that if he actually started doing it, he'd be killed very quickly. He may have been right. I think the times may be a little different today, but I think at that time he may well have been right. But anyway, that buried the anti-gravity experiment. And Sweet later died, of course, some years later, and carried the full secret of activating his magnets with him. I know 90% of it, but the magic 10%, I'm sorry, I just don't know. The best at working with somebody else we've been able to do is to activate magnets for a year. Oh, excuse me, sorry, 5 weeks, a month and a week. And they would gradually lose their activation all this time. But a Sweet, when he activated the magnet, it was there unless you hit it with a hammer or something like that. It really didn't lose it unless something really shocked it. But I've known several other inventors also and people and researchers who've tried to build it and who have succeeded in activating the magnets. Self-resonance in magnetic materials is now known in the textbook, particularly in thin film work. But getting a big old barium ferrite magnet to where the self-oscillation and the negative energy, binding energy of the barium nucleus going, that's something else. But to prove it, I once took a Sweet conditioned magnet. Now the B field, the magnetic field of the magnet is waving to and fro. You can take a piece of shim stock or a straight razor blade if you don't have anything else and put on this thing and turn it loose. It'll sit there on the surface of the magnet and wave to and fro like this, fanning air all the time, doing work. There's nothing but a shim stock sitting on a permanent magnet. I took that magnet with that waving shim stock, I locked it in a safe that he didn't have the combination to, with a combination on it, and I left it there 24 hours. And I came back the next day and opened it up and looked in, and it's still sitting there doing this after 24 hours. So was it an activated magnet? You bet. I don't know any permanent magnets you can go buy that will do that. But unfortunately, that activation process, all but about 90% of it died with Sweet because I don't know the other 10%. Walter Rosenthal knows a good bit of it. Walter built the device that he used to control his activation. Sweet never told him every signal he used, but he knows the main procedure by which the activation is approached. So he knows a good part of it too. And Walter's a very good man, very good instrumental specialist, very good engineer, excellent man. So one day maybe we will see folks resurrecting the Sweet vacuum triode amplifier. But as of right now, there's not one available to do the experiments. But we did get to do it. We did get to involve the heaviside component where we got a lot of effect, and we did get the anti-gravity effect significantly. So we had enough at least to tell us that we were on the right track with the whole theory and the other things that we talked about that we want to use now for looking at the dark energy effect and the dark matter effect and then the drag on our spaceships out there in space.
Okay, I guess we should talk about gauge fields, the idea of a gauge field, and how in this instance, in say for conventional gauge theory, that the gauge field or the A potential that we use is not a physical field, whereas in say higher symmetry electrodynamics like O3 or something, the gauge field that we're using there has more degrees of freedom and has a very physical significance to the system that we're talking about.
Okay, that's a good one.
So what we have in say gauge field theory is we start off with say a gauge field, and we have this way of saying that we can include this gauge field within the system of mathematics, and we can have the dynamical sets of equations that we use to be invariant under changes of this gauge field. So we have the freedom to regauge or change this A potential without affecting the physical dynamics of the fields that we're incorporating it in. But in the case of, say, high symmetry electrodynamics, we have this case where the degrees of freedom that are contained within the A potential we put in these equations is a lot greater. For example, in say, conventional electrodynamics, which is what we call a U1 theory, you only have 2 degrees of freedom, or 2 polarizations, the conventional sort of electromagnetic wave graph. But of course, when you go to O3, you get say the inclusion of longitudinal oscillations, say like the B3 field or something, or if you're considering other higher symmetry fields. So in the case of when we talk about say regauging or this sort of precursor engineering, perhaps you could give an example of how it is the case that by regauging those fields, we can sort of change those, or change those precursor fields to in effect get them to do more work than you would be if you left them alone.
Very good, and that's a very, very accurate point, because we do a very strange thing in electrodynamics, because historically, way back, if I go way back to the time when there was only about 3 dozen electrodynamicists on Earth, Maxwell had his equations out, but there were not very many electrodynamicists, what we would call electrodynamicists today. There were only about 3 dozen on the planet. And so it wasn't that we've got hundreds or even thousands of people working this at all the universities. This had not come along yet. So they had not discovered the electron yet. We didn't have most of particle physics born yet. We didn't have relativity born yet. And at the time, nobody thought that the potentials had any reality at all, except Maxwell himself. Everybody thought the potentials were just mathematical figments to help with the mathematics. And that the only real thing, as you said, the only reality was the force fields. Everybody was for force fields. Today we know there is no force field in space. But they had a material ether. Everybody also believed in material ether, which a thin material fluid which fills all space. There's no point in space, in other words, if you assume this ether, where mass is absent. Well, if you have a change there, you have a change in mass, at least in the luminiferous material ether. You're going to have force then. So it was absolutely natural for them to assume force fields in space, because they were really assuming force fields in the material ether. Well, the material ether was destroyed and annihilated experimentally in 1887, and some more follow-on experiments validated it. But they never changed a single equation, all of which assumes the material ether. Just one day, they got up and they sort of announced, well, there's no material ether, so we're not using one. But they never changed a single equation. The electrodynamics taught in classical electromagnetics and in electrical engineering today at all our universities still assume luminiferous material ether over 100 years after it was falsified. They also assume a flat space-time because general relativity hadn't been born. Well, we've known since 1915 now that's false. It assumes an inactive vacuum because most of particle physics hadn't been born, and today we know that's false. So there are many serious flaws in the present classical electromagnetics theory at U1 type that's taught at university and electrical engineering, because physics has learned a lot of science since then, but the models have not been changed. The models are still based on all those other assumptions. But what they did do when they did regauging, the equations as they turn out, quite a bit nonlinear, and they're awfully hard to solve. It's hard to get closed solutions. Normally you have to use numerical methods if you leave them alone. And so when you didn't have computers and you didn't have computer programs like Mathematica and so forth, numerical methods were bare. It was a lot of nitty-gritty, long, repetitious handwork, and you'd go page after page after page. To try to get through something very long without making some small mistake was very difficult. So it really was arduous to try to use numerical methods. They really needed equations which could be open to closed solutions. You could get closed solutions, function solutions for them. So they said, well, if the potentials don't matter, they're not real. It's just a mathematical game we're playing.
I suppose it's also interesting to point out there when you talk about the physicality of the A potential. I guess you could say, if you approach a conventional physicist, he will tell you that, say, in Lagrangian, when you take the covariant derivative, that in a similar sense in general relativity, you have a similar form where the A potential is replaced by a Christoffel symbol, which is
Yes.
relates to curvature of
Yes.
space-time. And he will tell you, well, we don't see that the A potential has any relation to curvature, so therefore, since it sits in that spot that curvature would usually take,
That's right.
then we're going to consider it, not physical, and we're going to consider it as just a mathematical convenience which we use.
That's right. And particularly even before then, before 1915, Lorentz regauged the equations. Actually, it turns out Lorenz with a Z regauged them before that, and Lorentz did it later and took most of the credit. And I refer to Jackson and Okun's paper where they point all this out. It's not me. But it was done before he did, and they always gave the credit to him because he did it later, and he was a very famous scientist, and the world sat up and paid attention when he did it. But the problem was we needed a closed solution set of equations where you could easily solve them algebraically and not have to beat it to death numerically with very slow, painful methods. So they said, well, we've got these two potentials, if you express it in potential form. We've got this A potential, and we've got this phi potential, and everybody knows potentials now are not really real. It's only the force fields are real. I can do anything I want to with these potentials to change them, so long as I don't change these net force fields. It'll be the same system. And if you believe the potential is not real, that would be a true statement.
Sure.
In other words, if it's just mathematics and has no reality, no physical thing back of it, that would be true. But it isn't true, it turns out. We know that from quantum mechanics now, but it wasn't born yet. So what they did is they changed the A potential, which means you get an extra force born for free also in that change. Now you have just changed the potential energy of the system. To change a system's potential is to change its potential energy that's in the system. That's okay. Change of energy magnitude is free. That's just energy transfer from some flow. Energy occurs in flows, not fixed chunks. And so it's okay because you just said, I'm going to collect more of the flow, and so I'll have more collected in the system. But I'm also going to get this crazy extra field, force field, and I can't tolerate that because I will have changed the system. So I will change the other potential, the phi potential, so that I'll make another force and I'll adjust the changes so the two forces are equal and opposite. And that means vectorially they sum to a vector 0, and therefore I can ignore them. No, that's the error. That is wrong. What I have just assumed is that I changed the potential energy of the system twice, but I trapped it in a stress potential. I used it to make a stress potential. That energy is there in the equations assuming that. But it's now locked up as stress. There is no net translation potential, force. No net translation force. But every force was created. Those two equal and opposite forces are still there. And their energy is there.
A good example is to use, like you were saying the other day, if you take a football and you put pressure on it, the ball is not moving, nothing's happening, but the stress energy there.
That's correct. You've increased the stress energy of the football. Otherwise, you can't validate conservation of energy. If you check the energy being put in, and it's got to be doing something. But anyway, once they did that, the potentials were changed. Both of them were changed, but the net forces, net translation forces, did not change. And so at that point, they said, well, we have the same system, no problem. So they did that in a deliberate fashion, keeping these two forces arbitrarily, keeping these equal and opposite, and they changed it so that now we have extra stress energy, but no extra translation. We don't have anything extra that'll push extra electrons in our system as current through the load and power it for free. We got the energy, but we've locked it up where we can't use it. So, and they said that's the same system. It's exactly the same as we had. It isn't. It has more stress. But by doing that, they were able to have a system which now has algebraic solutions, and you don't have to do numeric. Most of the time you can do algebraic and seldom have to resort to numerical unless things get pretty nonlinear. And so what we did is we built a system that was much more facile to handle and so forth. But as far as what the actual systems are concerned, here are the assumptions we went through without labeling them. We assumed, and the gauge freedom axiom to this day still assumes, that we are free to change the potential energy of any system we wish, whenever we wish, for free. In other words, it assumes energy is free for the taking. Let that sink in. And we've got an energy crisis, and we've been assuming for 100 years that energy is free for the taking in any system. Yes, that's true. But we will always be such a fool that we will change this free energy twice, and we will change it just so it locks itself up with the forces, and we don't have a net translation force then to use that energy and dissipate it in the electrons and power the load. We have the energy, we have the excess energy, we got it from somewhere, we'll have to run down where the source was, but we locked it up by our own intention as stress energy where it doesn't have a translation force to dissipate it and produce power in our circuit. This is the kind of electrodynamics and electroengineering we have today. Now, the problem is you've got to have materials and systems do this for you. You can't just make the model. If you don't build that system right, it won't do that necessarily. And the way you do it is you design a standard circuit which always has forward EMF equal to back EMF. In other words, the force fields will be exactly equal and opposite. And that's called the standard closed current loop circuit if you wire in the external source of potential energy. Because the moment you make the source produce current, you deplete the source. You use half the energy collected in the circuit to do nothing but destroy the dipolarity of the source. And so by doing that, we have a theory which insists that we're not going to have any extra forces around for us to freely use and power the load for free. And we build a circuit which guarantees it self-enforces Lorentz symmetry and invariance. The equations are invariant. Now let's talk about invariance. Invariance, amongst many other things, means that no net observable appears. So if I have an invariant theory and I change it to another set of invariant equations, it means that I did not allow any net observable to appear, any new observable. A new force would be a new observable because you could stick something in and watch it happen. So what they did was reinforce invariance. It's Lorentz invariant, Lorentz symmetric, and they call that symmetrical regauging. Now there's no law of nature requires this. This is totally arbitrary human decision. If you're free to change the potential, there's no law of nature says I have to change both potentials. There's no law that says I have to change them just so that they each produce equal and opposite forces and lock up all the energy of stress. That's by my own intention whether I understood what I was doing or not. And suppose I say, well, crazy fellow that I am, I want to use this energy. You say I can have it for free? I want to get it on for free and get some of it in. I'll have to pay for some switching and control, but I want to get a lot of it in for a little bit of investment. And then I want this energy to come in a form where I can use it and direct it to power this load, where I can get some work for free. I can do like my home heat pump. I can get 3 or 4 times out working the load as the energy I have to put in. All the rest of it's going to come in through regauging from the environment. So that's what I want to do. Well, then what am I going to have to do? I'm going to have to break invariance. Invariance says you will never have a free force to power your load with.
In this case, you mean Lorentz invariance.
That's right. And so I will have to break invariance, Lorentz invariance, which means I have to break Lorentz symmetry, which means I can't have the back EMF equal to forward EMF. And which means I also can't wire in and leave in when current is flowing the external source of potential. There's certain requirements that come out of this once you say clearly what you wish to do and why. And my purpose is to get some extra energy for free or almost for free. I'll pay for the switching and control. But I don't want to have to pay for putting all the energy in. So my purpose is to get some energy in a form in the system where the system has some forces now that it can use to drive that and dissipate it in that load and power it. And I only want to have to pay for switching and control. I do not wish to have to pay for all this energy. To do that, I have to break invariance. If my circuit does not break invariance and Lorentz symmetry, forget it. I have to have a model which breaks invariant. If I took the equations and I symmetrically regauged them, forget it. My model says you can't do this. You'll never get any energy in from your external environment for free. Everything you get in there, you will put in there.
So just to sort of distinct the two, sort of symmetrical and anti-symmetrical gauging.
That's correct.
So what we're looking at is a symmetrical case is where you lock that energy up in force by 2 opposing forces, say in the ball effect.
That's correct.
But asymmetric is having one of those which is a little bit different, so you
That's
can have
correct.
then a translation force on.
Exactly right. I go back to how they made the forces equal and opposite. So my requirement turns out to be very simple. The regauging I do has to make the forces not equal and opposite. They can either be different directions and have a net resultant, or they can be not the same strength and have a net resultant and still opposite in direction, or several other variations. But I must not have them equal and opposite. That's the main requirement. That breaks invariance when I do that. It also breaks Lorentz symmetry. It also gives me some free new observables, that's observable forces, and some new free potential energy in the system. And now I have a force to take this potential energy and expend it in a load, and I can get free work out of it by paying for the control and switching. I haven't violated physics. Now, I've violated a lot of people's idea of what physics is going to be forced to be, but I have not violated physics itself at all. I have not violated thermodynamics. I did not claim that we created any energy out of nothing at all. I said it came in from the environment through regauging. We go by how we get that in from the environment. If I get it to come in a shape where I can use it and can direct it to power, energy, and load, I have something analogous to a common ordinary home heat pump. Absolutely permitted by thermodynamics and by physics. I haven't violated anybody's rules. I haven't violated conservation of energy at all. So the question then becomes how do I go about changing the back EMF and the forward EMF, making them not equal? And the main thing is, how do I potentialize my circuit? All the energy in the circuit comes from the potential. The standard little simplest formula in the world, W equals phi Q, for example. Whatever my phi is, my voltage, that I have voltage difference, potential difference that I have across the circuit, onto how many static charge, actually fixed and not moving, no current flowing, that's how much energy those charges will collect. That's W in joules. So what I wish to do is I wish to have this circuit absolutely sit here and not move at all, allow no current momentarily. I want to connect my external load. I want to flow the potential across the circuit, potentialize all of those electrons. Every one of them gets its potential charge. And it's now excited. It's now an excited circuit. And then I want to switch this. I've drawn no current from the potential. I haven't changed this potential source at all. It'll flow potential from now till the end of time if you accept no current from it. So what I want to do is separate the source potential. I want to leave this gap. I want to plug in, say, a diode. I'm using an example, a diode and a resistor. And then I want to sit back and have a magic switch. Either the circuit switches itself or I have one to throw, where now energy can flow in the circuit. And at that moment, when that current starts to flow, this circuit will depotentialize. It will decay, discharge. It will power the load freely with some amount of energy. And then I do it again and again and again. I can get more energy in the load, and I don't violate any law of physics and any law of thermodynamics than I have to put in myself, just like a home heat pump. The energy is input. It's just that I personally do not have to input. The efficiency of the system is not greater than 1. No system does. But COP is permitted. You are permitted to go greater than 1, even to infinity. You can have the environment put in all the energy, like a windmill.
So I guess at that point, is it sort of necessary to sort of classify a distinction between what we would say to be sort of observable physics, the stuff that we would say where you can form closed systems and you can, look at, the conventional law of thermodynamics, etc., compared to, say, like the virtual state system, where if I say this is the collection of all observables that we see, the physics, houses, people, all the things that are going on that we see, and this side over here is the virtual system, where there is some bleed of information between these two guys. And of course we see that with dipole systems and charges generating field information from from essentially nothing in a way, but it's not nothing if you take into account this virtual state system.
That's correct, and that's a very good point, because when we talked about invariance and we talked about breaking invariance, we really said in effect that we're going to have an extra observable appear. Now let's reason together. If I have no observable input and I have an extra observable appear in my circuit, then there's only 2 explanations that are possible. One, I created energy out of nothing at all. The circuit did. Okay, if you do that, you got to give up the entire conservation of energy law, destroy most of physics, and that is not true. We've got too much that shows energy is conserved. So that's out.
Sure.
So we didn't create any energy because that's a non-viable option. The only other option that's there, since I had no observable input change, is that I had to have virtual energy input. I must have the energy input. Now, the laws of nature do not say that I have to have this energy only in one form. It says you can have it in any form you wish to, as long as you transform it to the form you need. Well, let's pursue that a matter. Let's talk about now the difference. We've got to be very clear about the terms vacuum energy and zero-point energy. In quantum mechanics, if I have an oscillator going and I cool it down in temperature and all of this to absolute zero, classically, you know, theoretically, all the motion stops and there's absolutely nothing going on. It's absolutely static. That is not true in quantum mechanics. In quantum mechanics, there's a residual motion that remains. It's the lowest quantum state. But it's still real and it's still observable. It didn't go away. And because of the zero temperature and all that, we call that the zero-point energy. So when I have a better model or a model to look deeper into the smaller parts of a system rather than so high in the classic area, I now find that I do have zero-point energy. That is energy that's left when everything else classically would have reduced to zero. But it's observable. So it doesn't meet the criteria we just talked about. It is not energy that's non-observable. So my problem is I've got to go one, that's where all the thermodynamics stops. They start with the energy when it's already heat, it's already in observable photons. We have just said to do what we wanted to do with our system there, we had to go one step further than the observable state. Otherwise, we'd have to be creating energy out of nothing, and we are not doing that. This drives us then to what is called vacuum energy, loosely. Many people misuse these terms. They are not the same. Now, what we mean by vacuum energy, quantum mechanics tells us the vacuum is subject to all kinds of little fluctuations. You can have any amount of energy as long as the time is short enough, it's less than one quantum of action, of change. As long as it's less than a quantum of action, it will not be observable. No instrument will measure it. It will not produce any physical effect by itself. And so when you look at the vacuum with your instruments, you won't be able to find these little fluctuations. But the energy can be enormous, and they occur at such an entire rate. We ask ourselves then, what would be the density of all this completely disintegrated energy, completely disordered energy? What would be the intensity of it or density of it if we could measure it? Well, what we are doing is assuming that somehow we could cohere it and integrate all of it together and say what would be the intensity of that if it were integrated. It turns out to be extraordinary, incredibly large. So large it boggles the mind. I mean, 1 cubic centimeter of vacuum, depends on who makes the calculation and the assumptions you make in it, but an average kind of good calculation will start with a cubic centimeter of vacuum about the size of the tip of your little finger. And there's more raw energy in that if it were cohered and were collected so you could measure it, than is in all the observable mass in the universe. Wow. Now this is people like Wheeler. This is eminent physicists now making this. They disagree with a little bit of the assumptions, and one will get 10 to the 90-something, converting it to mass, grams per cubic centimeter.
Sure,
the other will get 10 to the 120th, but okay, that's good enough for government work. It's a big number. It's good enough for us to say, if I can get the tiniest bit of that, I can get all the energy I want right out of the vacuum. So what is my problem? My problem is I must find some way to coherently integrate, and also reorder this totally disordered virtual state energy of the vacuum. Now that's been considered such a remarkable thing that nobody's even looked at how to do it. But they have also remarkably refused to look at the fact that the source charge, once you produce some charge, any kind of charge anywhere, and fix it, it's nailed on a bench, it's not going anywhere. And it's isolated, that is, nobody's putting photons in here. This thing will sit here and you can take your instruments in the line and you can measure the emission of real photons, real fields, real potentials at light speed from it in all directions. And it'll keep going till the end of time if you don't disturb it. The original matter in the universe, the charges have been pouring out real, observable, honest-to-God energy for something like 13 billion years or so. So have all the dipoles. Well, in particle physics, we know that opposite charges do have broken symmetry, which means something virtual had to become observable. Some kind of integration had to occur. So we have plenty of things that are telling us that we do have integration, like broken symmetry is one in particle physics. So how does it do it? What's the mechanism? Well, we looked for 3 years for fantastic esoteric mechanisms and all kinds of nothing worked. We went back to the old source problem, the old source charge problem. I have a charge sitting here, and the darn thing pours out energy all the time. Real, honest to God, measurable, real photons, observable photons, making its field, it continually replenishes the fields at the speed of light. They appear to be static. They're actually steady state flows. It's a steady state, non-equilibrium steady state system. There's no observable input to it. The only input to it, if we want to keep the conservation of energy law, it has to be virtual. But the virtual state's disordered. It has no order. There's no formation of an observable photon in this vacuum. Stuff that I'm looking at is feeding the charge. But let's see what a charge does. The charge in particle physics goes past the charge in classical electromagnetics. Classical electromagnetics, you got a charge in empty space, no interaction. Empty vacuum, no interaction. There can be no input to it from the vacuum or space. So you're dead in the water if you're using classical electrodynamics. It doesn't even have an active vacuum, virtual or otherwise, for you to get any energy from. But if I go to particle physics, that's not true. I've got all these fluctuations, so I have plenty of fluctuation energy. Let's look at one aspect of those, photons. I have all these photons, some high energy, some low energy, appearing and disappearing. Incredible rates. Total energy density, if they were integrated, is so fantastic that you can power the world with it. So what happens? How do I get it integrated? When it is absorbed by the charged mass, mass is unitary. It turns the energy of the photon into mass, divided by c squared, standard relativity, and we have the change in mass. Well, it's already so tiny in a virtual state it's subquantal. So I really shouldn't call this a delta M. The change is more like a differential of M. It's real tiny, but it's not zero. It's still immeasurable, but it's not zero. It's merely a differential, partial of M. So this next one, they're absorbed, rapidly, one all the time. So the next one that's absorbed adds another little differential. Mass is unitary. You change the mass that was there when it absorbed. The first M plus differential, you get another differential added to it. The differentials add coherently. And so the mass is changing, still in a virtual state change, until it reaches the quantum level. Finally, it'll build up to, there's enough mass energy here. Were it a photon, it'd be an observable photon and take off at the speed of light. We know that mass is getting a terrible buffeting from the virtual particle beating of the space and everything that's embedded in the vacuum. We know that the charge itself, the electron, is not sitting there as a hard object. This beating is knocking the daylights out of it, and it's being forced to change in all kinds. On the average, it's an electron. But it's gathering everything in between, and so it means it's turning into photons every once in a while. When it turns into one that's an observable photon, you just lost one. That buffeting knocked it right out of there. And it takes off radiating an observable photon, collapses abruptly this excited state, and it goes again, fires another photon. And it's getting them from every direction, so it's firing in all directions. And statistically, for extraordinary large numbers like that, we'll have a deterministic field intensity for the field as a function of the radial distance, and same thing for the potentials. Now that's interesting, because I started with total disorder, which is a zero symmetry state, which is still a state of symmetry. It's not non-symmetry. And it's a zero state of order, which is still a state of order. You can't neglect it just because it's zero. It means you can have a broken symmetry of the zero symmetry state, or of the zero order state, a disorder state, and you can turn it into order. That's what breaking disorder would be, have some order. And the coherence would be there. It's already there on the particle. This thing is a totally negative entropy operation. It takes totally disordered virtual state energy and turns it into the emission of ordered field energy. And if you wait long enough, it'll reach out and spread out across the whole world, observable world. From the original matter, it's already across there. And so wait long enough you want to is how much energy is in it, how far out it is. So every charge in the universe is doing the magic that we needed. It is a totally negative entropy, and we can produce it and prove it in a laboratory because we can observe the effect of it. We can measure that field and the determinism of it. we have just destroyed the second law of thermodynamics if you go past the observable state and also include the virtual state. Now, normal thermodynamics does not do that. They stop at the observable state. They do not have that extra input, nor do they have that negative entropy state input. So the second law applies. There are certain things we know that violates it, but the violations are very few, and they're still working on it. The second law has held up pretty well so far. But if we include the virtual state, we have an immediate falsification of the present second law. We don't throw the second law. It fits so many things. We don't throw it away. We extend it to include the case that it no longer describes. And that's real simple. We've shown how to increase it. All you do is permit negative entropy operations. So basically the converted second law says you can have either negative entry, departure from equilibrium like you have in any fluctuation, and you can have return to equilibrium, which is a totally entropic operation. You can have negentropy or entropy, and they normally occur serially. In other words, I'll have first the negentropy part of it, which the charge first does, and then it pours out to the fields, and that produces a new symmetry and new order. Well, I got another problem. The Klein geometry that we've been using since 1972 doesn't permit that kind of reordering. The geometry itself says if I break symmetry at one level, I lose all that information and I drop down to the lower symmetry. I can never increase the symmetry. So it really prohibits that. Well, we now can do this experimentally on the bench. We can show that we do it, and the world does it. Every charge does it. So we got to change the Klein geometry. We got to go to something like Layton's object-oriented geometry, which does allow it. With better group theoretical methods, now more advanced, and looking at problems that deal with, like, certainly have to be dealt with in robotics and some other areas, he came up with an improved geometry called object-oriented geometry. And it has a very unique characteristic. When I break symmetry at a given level, I keep the information, don't lose it. So I've still got my lower symmetry, I didn't lose that. But it also creates a new higher symmetry at the next higher level. That's called orders, hierarchies of symmetry. His geometry comes out with hierarchies of symmetry, which is a negative entropy permitting operation. It prescribes you have to have negative entropy to get that next higher order. You had to reorder to do that. So if we go to latent geometry, or that type of geometry, and if we include the source charge solution, we get the coherent, how in the world you can coherently and reorder and integrate to observable form the actual virtual energy of the vacuum, the disintegrated energy, not the 0 point energy at all. And bingo, suddenly you have an inexhaustible energy source, and that's the way to go. Because every charge in the circuit is already doing that. That's where the energy comes from. If we take a generator and we crank the shaft of the generator, it doesn't have anything to do with powering the circuit. Let's trace it. I add mechanical energy to the shaft of the generator. The generator turns. Once it's in rotation, all that mechanical energy is transformed into rotating magnetic field energy. That's a change of form of the energy, that's work. So I have to do work to crank the shaft of the generator to produce that rotating magnetic field. All the work I put in is gone the moment I get the rotating magnetic field. And I lost some. It's not a 100% efficient system. So I had to put in a little more than what I got. Well, what does the rotating field do? Does magnetic field go sailing out of the terminals of the generator and go sailing off just pure magnetic field? Nope. What it does, you expend all that magnetic field energy on the charges inside the generator. Force negative charges one direction, positive charges the other. Now, admittedly, you've got to rearrange through your connected circuit all the charges, but you polarize the entire circuit. Now, once you polarize it, it's all excited. The potential has flown down the circuit. There's plenty of energy in the circuit. In fact, there's far more if you count the heaviside component than anything you dreamed of inputting by cranking the shaft of the generator. And it all came right out of the vacuum by these charges you forced apart, because in particle physics, opposite charges are a known broken symmetry. They do produce new observables, real energy. And so particle physics agrees with it. A Nobel Prize awarded to Li and Yang in 1957. That's one of the broken symmetries. So what really powers the circuits anyway that we're building is the same energy from the vacuum that we were just talking about, the disordered, disintegrated virtual energy, not the 0-point energy, being reordered and integrated coherently and turned into real photon energy by the source charges. Once I get those things separated, the differential is going to give me the excitation and the energy collected in that external circuit. If I will leave that source dipolarity alone and not touch it, it will pour out energy till the end of time. But if I let current flow all the way back through it, half of the energy collected in the external circuit will be used to do nothing but destroy the polarity that I just paid to make. Since I have a less than 100% efficient remaking the polarity, I will always have to put back in more energy to restore the polarity that I foolishly designed my circuit to kill than I'm able to get out there in the load. So I'm always in under unity. And that's why every system we build today is so. I pay the power plant and the power company to have a giant wrestling match inside their own generators and lose. That's what we pay them for. We don't pay them to think and think of modern physics. So the point is, all of this stuff, breaking invariance, going after the virtual state energy, even though it's tremendously disintegrated and subquantum, I don't have to discover how to extract energy from that and coherent. There is an object built by nature itself and given to us in unlimited quantity everywhere, easily handled, easily created and set up on a bench, that will do that forever. All I have to do is learn how to correctly use the little energy gushers, the little oil well gushers of this vast energy oil field that nature's given us. And that we have yet to do.
Maxwell did quite a complex construction of electrodynamics. He used what Hamilton came up with as the idea of quaternions, or Maxwell called them fermions, because quaternions come in four objects. Okay, and now the mathematics of quaternions compared to vectors or even conventional numbers is very different. They behave differently. They have a completely different, what we call a different algebra, and there's. Because of the different algebra, quaternions have a very different mathematical structure, which means they can contain more information from a system. Okay, they contain, in terms of Maxwell's equations, there are 20 equations which you get if you have the quaternion structure. Just to give you some example or reference, the conventional electrodynamics which we use today has only 4 equations. So what you've done in essentially going from, chopping off the bits from quaternions and doing some other alterations, you've gone from 20 down to 4, so you've lost 16 of your equations. So that's a lot of information loss. Okay.
Can you talk a little bit more about what was in the 16 equations that disappeared?
Well, the 16 equations is really, say for example, that relates to the highest symmetry O3 as compared to, say, U1 for conventional electrodynamics. It wouldn't really relate to it, other than just saying, because you see, in order to describe that, I could describe, say, what Myron uses the B3 field, which is a longitudinal part of the wave. Mm-hmm. That comes in from the quaternion construction.
And is one of the discarded 16 equations?
This is, if you don't have quaternions, you don't have the B3 field.
What I'm saying is, of the 16 equations that Heaviside threw out, what was their what was it that they expressed?
Well, these are just dynamical equations of fields which describe the way that the fields interact relative to one another. Like conventional electrodynamics, you write down the field equations, but they're all fields in terms of each other. It relates the E field to the B field, etc., and so forth, which is the electric field and the magnetic field.
Is there anything about those 16 equations that comes into play with what Tom is talking about? What we're dealing with?
Yeah, certainly. The B3 field. Well, the B3 field is just one example of, more variables. One of the extra variables you get in, Maxwell's equations.
There probably weren't many electrodynamicists who continued on with Maxwell's original equations.
I don't believe so. I don't know where. A lot of Tesla's papers are out of the loop. So as to, the stuff that he was using was certainly contained, as far as I understand, in the quaternion formulation of electrodynamics. You can't get those sort of effects otherwise.
That makes sense. I mean, it's a sensible.
Yeah, sure, definitely.
Well, and Barrett's work indicates that as well.
Yes, I think so. Quaternions really are a very powerful way to enlarge the structure and the information content of your model. It really gives a new type of aspect to the way the fields behave as well. So you're allowed to have these very strange, say, longitudinal oscillations. You're allowed to have odd things going on which you don't see in normal electrodynamics. I would say that a lot of the effects we've seen so far need some work to understand exactly how those extra components are working and operating. But I do believe that the information which we're looking at is contained in the quaternion structure of electrodynamics. Obviously, I don't think that's the final sort of holy grail of everything, but it's a very big step to getting the huge portion of physics which is missing essentially from conventional views of electrodynamics. Okay, so quaternions are sort of what we call. Let me just draw an axis first. Okay, so if I'm going to look at any kind of physics in this two-dimensional arena that I've defined here, what I'm going to do first is define what I call a basis component or a basis vector. Say, for example. Okay, I'm going to make this. I'm going to call this E1, and I'm going to call this one E2. Okay, so whenever I write, a position in this space, what I'm going to write is the position of this point here is going to be equal to x1 E1 plus x2 E2. That defines a vector representation of this point here. Okay, and these things these are basis vectors. Okay, and these have a very well defined behavior with respect to each other and so forth. Okay, so that's a vector. Okay, with a tensor, that's a little bit different because what you're doing now is you're combining these elements. Say, for example, in electrodynamics, we have what we call a force tensor. Okay, and if I write this turns into something which is well. Let me define first that I can write this as this is just purely another way of representing what I have here. I can write this as x1, x2, an object like this. So it's like this is what we call a vector matrix representation. Okay, with a tensor is a little bit different because you're not only having information components in this direction. Say, for example, I have something which is now looking like this: x1, x2, x3, x4. I've got extra information about the system, where tensors will allow you to describe, for example, things like twisting, stretching, that kind of thing, where vectors will only describe to you, say like the point, the velocity, etc., etc. So the force tensor, for example, electrodynamics, or even just conventional mechanics, will allow me to describe the stress of the system, twisting of the system. Quaternions are a little bit different now because what we've got now, instead of these basis vectors here, if I write a quaternion equation, what I've got is x now is equal to x1. I'm going to write quaternion 1 plus x2 quaternion 2, and these are not the same as these things. What we call a quaternion algebra is very different. Now, what I mean by an algebra is, say, for example, the number of the algebra of numbers, which you're familiar with. Say, for example, if I take 1 times 2, that's equal to 2 times 1. Okay. Now, in quaternions, that's not quite different, because if I take a quaternion labeled A, and I could take quaternion labeled B, this is equal to minus B times A. So that's not the same. So if you flip them around, you get a sign change. Okay. If I could write the full algebra here. If I write a quaternion like this is equal to 2, like this. This is the actual algebra which I'm looking at. What that means is the mathematical representation I use for, say, B or A is not a conventional, singular, like a number value. It's nothing like this. This has definite or an enlarged structure, if you will. And we have a matrix structure is a nice representation to use. So what that means is, because you have this enlarged structure, it means you can have more information content in your field theory, or the theory you're trying to describe, as opposed to vectors, which have essentially less information to them. If I have this vector approach, do I still have a valid set of equations which give me what I need? And to all intents and purposes, that was pretty much correct, and it still included the heaviside component. But again, of course, Lorentz had this trick of getting rid of the heaviside component, and then you have what we have today, which is the vector representation without the heaviside component, which is basically as watered down as you can possibly get version of electrodynamics.
Yeah, well, thus we have a very limited system of electrodynamics.
It is very limited, extremely limited. To give you an example, this what we call anti-commutativity relation. This is what we call an anti-commutativity relation between two quaternions. That very structure gives you fields which you don't have in the vector formalism. For example, what Myron Evans is dealing with, the B3 field, right, which is if I draw a conventional electromagnetic wave, okay, this is the E field, and this is the B field here. Okay, if I have this system, if you have this system of quaternions, what you in fact have is a longitudinal oscillation called the B3 field as well, along here. So you've got an extra degree of freedom which is introduced into your equations, which can introduce some vitally different physics to what you're used to with conventional E and B fields. So it's almost in a sense you're just saying, well, okay, I'll take this first model and I'll discard a lot of physics and pretend that that's not relevant to what I want to do anyway. And to a large extent, it's not. We know that conventional circuits work and work pretty well, but of course you're missing stuff which could give you some potentially new phenomenology. I think it might be worth also mentioning this, perhaps discussing that on the issue of sort of dark energy, the idea that when I take quaternions, which is the sort of
yes.
The idea that when
got to get to symmetry or we're not there.
We know that the universe is expanding, and from that we know that it's not just expanding but accelerating. Now, so you need some description of your universe which encompasses that. Now, in conventional theory, you have to plug in cosmological constant by experiment, and there are 3 different distinct types of universes. But with quaternion structure, if you impose that on GR, you get exactly the one unique solution, and that unique solution allows an oscillating universe. And with an oscillating universe, it's a sort of sinusoidal action, and you will get variations in expansion. So it will be accelerating, decelerating, accelerating, decelerating. So you automatically have that formalism of expansion and contraction in there. So coming back to what you were saying about the holes, which are repelling and speeding up and accelerating the expansion of the universe. In quaternion GR, you get exactly that. That is exactly the unique solution for the type of universe that you have, as opposed to conventional GR, which only has
I think that's a beautiful lecture. I couldn't possibly add anything to that. That's beautiful. But it's absolutely true. If you do not use a higher group symmetry model, you do not have a model which can describe it in the first place. Your model itself will exclude it.
Exactly, yeah.
And if you judge the criterion by what your model says, by what the mathematics says, and you keep using that model, you will continue to say, you can't do this. Say, here, mathematically, you can't do this. It's impossible. Yeah. Well, that's an incorrect statement. What we should always say, it is not possible to do that within this model. And your return then can be, well, okay, then if we change the model this way, just as you went through, exactly, if we change it this way, then we can do it. So maybe we haven't been quite using the correct model. The other model is still useful for a lot of things.
Sure.
But for this particular case, we have found Gödel's limit for that model. We found some phenomenology it cannot describe. That means we simply find us a better model, as long as we're going to deal with this phenomenology. If we find one that can describe it and it fits experiment, we're in business.
It's another interesting thing to point out that when you include quaternions and you get this oscillating universe, that Neil Turk's group at Cambridge, they're considering what they call an ekpyrotic universe, which is exactly an oscillating universe. So it's interesting to see that somebody who sort of introduced quaternions in GR has now got the same effect, where you have the situation where the only unique universe, or the unique solution for the universe, is an oscillating one. And so what you have is this sinusoidal action. And coming back to what we're talking about with dark energy and so forth, with this idea that you have this energy in there which is like causing a pressure which is expanding the universe. So the expansion is accelerating. And when you look at a sinusoidal wave, there are parts there which gives you exactly moments of acceleration, moments of deceleration, moments of acceleration, and so on and so forth. So you get that effect from introducing the quaternions in GR. So that gives you the unique solution. It's interesting to contrast that with the conventional GR, where you don't have quaternions, and what you have are the 3 different solutions, and you have to put in by experiment exactly the cosmological constant, to match the universe that you're trying to observe.
Well, you know, there's another question that I think this pileup probably addresses eventually, but we don't right now. And that is the fact that, you know, things like the Big Bang or the inflation model, all this stuff, they all got one big problem. You should have created equal amounts of antimatter, and we don't find that amount of antimatter. There's a lot of missing antimatter in the universe by the conventional models. So where did it go? Well, maybe it got formed as holes rather than, you know, coming up above the vacuum. Maybe it went this way, you see. Get some positive energy, some negative energy. In that case, you would only have the antimatter that has grown out of interactions of the other stuff. You wouldn't have, you wouldn't say that for every electron I produced, I had to produce a positron. You could say I had to produce either a positive, well, I really had to produce a hole. I had to have zero energy net difference.
Because you can say also that the whole, in that sense, you know, because it's a little bit like pair creation, but you're doing it sort of shifted ways, aren't you?
That's right.
So in that sense, you know, that the spin statistics and, you know, the conventional notion of antimatter will still be the same, but the masses are just opposite.
Well, it appears that, you know, first of all, we do have something that can be done. You know, you can do experiments with it on the bench. A little bit of trouble and a little bit of change of the way you think with your mind and how you got to think with your instruments. You don't just measure it directly. You got to convert it and then measure it as positive energy. Maybe someday we'll have a good negative energy. Well, one of the first things you'd want to do is make an instrument that'll do that. Right now we can't go buy one. So the first thing, you can pick up the indications in a neon gas tube or a plasma thing. But first thing you want to do is get yourself a regime of measurements that you're pretty sure of. Now you know what you're measuring, what you're seeing, and why. You've got to have some idea of why, or you won't know why you got this excess energy and all this, and why it's not observable until you change it with a capacitor and so forth. But if we do that, we have the elements for building a science, you know, an experimental science, and then therefore technology. That's the beautiful part about it. We really do have, looking at us, the ability to build a technology and use it. The problem is, unless we can change the electrical engineering model and the classical electrodynamics models that's so widely taught, we will just never get the model, we'll never get that technology born. So we really need some kind of movement, enough experiments, maybe somebody does a beautiful solution to dark matter and dark energy and so forth. If we can get enough done to show the real need for it, then maybe we can start getting something done about changing an electrical engineering model and so forth, or at least up at the graduate level.
Sure. I think from a theoretical point of view, I think that quaternions are a very big way to go. I mean, they've already shown in Maxwell's enlarged equations, the 20 equations, applying them to GR and so forth, you get a wealth of information, and you know you're getting closer to this unique solutions without interference from, say, experimental insight. So I think that's a good. I don't think that's the whole story, but I think it's a very big way to go, the quaternions.
Certainly, starting with quaternions is a good approach because you've got a much higher group algebra right there than you have with tensors, for example.
Sure.
The tendency is to say if you want to start with something with tensor, other than tensors, there's something wrong with you. Well, that's not true. Barrett took a look at Tesla's actual patented circuit with quaternions, and he found things that you can't even see with tensor analysis. They don't show, but they showed very clearly in quaternions. So I think he showed us very clearly that you can find things in electrical circuits that are happening that you can't see with tensor analysis. So you should adapt the analysis tool to what kind of phenomenology you're looking for. If your mathematical tool can't even show it, you're never going to use your mathematical tools to find it. But if your tools show it, maybe they'll give you a lot of clues to what you ought to be doing in the circuit to see it. They'll tell you what you got to hunt for and look for.
Sure.
But that was beautiful what he did there. I don't know of anybody else that ever did that except Barrett. So an awful lot of it depends on your choice of model. Same thing with this geometry. If we really want to get into all of that sort of thing with the geometry, we're going to have to change from Klein geometry.
Sure.
You don't have that negative entropy in Klein geometry. It prohibits it. You can't get that extra symmetry. But we disprove that every time we form an ordered field from a source charge. So, you know, we got pretty good grounds to go on. We just got a lot of practice we got to overcome. It's a crazy world we live in sometime, but it's also a very hopeful world. The way most things change you get the changes in at the young stage. And some of your bright young fellows get fired up with that, and they go do some experiments, or they get an idea and go chase that theoretically, or a combination of both. And pretty soon you start to have discoveries. Once you have eased that iron boundary so that they're permitted to roam outside the fence a little bit, and they actually get a little funding for their postdoc programs and the graduate school and doctoral programs. Once you actually put some funding in it and allow a little bit of roaming outside the fence, you will start to get real ideas and real fruitful results, which will give you a new science, extend your science.
So, okay, so going back to this notion of sort of enlarging your structure of information of your theory, I think it's important to note that the difference between, say, having quaternions and, say, vectors, I mean, take, for example, with Maxwell's theories, you know, his quaternionic theory comes up with 20 equations. When you squeeze that down to a vector interpretation, you get down to the 4 conventional equations that we know today. Now, if you take general relativity, for example, and you apply quaternions to these, what you end up with is a greatly enlarged theory with a lot more information. And not only that, coming back to the discussion we had with dark energy, you know, this idea of you know, negative energy being resident in between the galaxies, pushing them apart, and not only expanding the universe but accelerating it as well. The unique solution you get for this universal scenario with quaternionic GR is exactly that case, that you have an oscillating universe. And so if you look, an oscillating universe will be a sinusoidal action. And if you trace that sort of along the sinusoidal path, you'll get sort of paths of acceleration, paths of deceleration, and so on and so forth. So you get those periods exactly as you know, so you get this notion whereby this scenario of, you know, universal expansion acceleration can be exactly encompassed in the unique solution that you get from quaternionic GR. Now, you don't get that in conventional general relativity. You have to put that experimentally in by hand in what we call the cosmological constant. And it's also interesting to note that there's some groups, most notably Neil Turek's group in Cambridge, and they're considering what they call the ekpyrotic universe, where they have a scenario where it is exactly oscillating like this. They're no longer considering just a scenario that we have a big bang, we accelerate, and that's all we're considering. They're considering that oscillating universe. So this is sort of like a clue, in a sense, that's saying, hey, you know, if you enlarge your algebra type, say in this case from vectors to quaternions, you're getting so much more information about, you know, the dynamics, the possible scenarios. And, you know, the key point here is the fact that in conventional GR you have 3 distinct types of universes that you can have, but in quaternionic GR it says no, you can only have one, and it's not only one, it's one which is oscillating, and one which kind of fits the bill that we're looking at in, you know, inflationary and accelerating universe. And also to note on in the idea of enhancing your symmetries, if you take in conventional gauge theory this idea, say for example U1, conventional electrodynamics, if we take this, what we have is a scenario where we can write a set of equations which govern our dynamics of, say, a system we're considering, the Lagrangian we'll call it. And within this we can define what we call the vector potential. Now this has the freedom to be regauged or changed in some way. You can add a piece onto this, which is called, you know, the gauge term. We can change this potential. But what conventional wisdom will tell you, well, you know, this gauge potential can't really be real, because in a similar sense in general relativity we can define a similar equation where the bit where this A potential occupies is what we call a Christoffel symbol, and this relates to the curvature of geometry and so forth. And of course, you know, this by sort of assumption can't happen, because we can't have a potential, you know, being physical, because then we could somehow relate that to, you know, changing curvature in space-time. But what we see is if we in sort of enlarge the symmetry, I'll take for example O3, which is, you know, in some sense, you know, a quaternionic extension. What we see is that we can actually have that interpretation, that A potential, the slot in which it fits, exactly can be related to curvature in space-time. This comes back to what you were saying in symmetrical and asymmetrical regauging, in the sense that we're using curvatures around the space of the charges that we're looking at. And we can exactly get that process of, you know, you now have a potential where we can consider that is exactly related to the curvature. So we can use this idea of, you know, in symmetrical regauging, of course, you don't have that, but asymmetrical, you know, you have, you know, a difference, so you can have that translation. So in other words, you know, this idea that when we go to higher symmetry properties, we've now admitted the idea that we can now have, okay, we can have a potential, and as you say, you know, the potential is allowed to be regauged or changed, So we can have this idea of, okay, we can now change curvatures in that way. We can do work, and we can do sort of energy from the vacuum physics in that way. So the next step is to consider, well, when you consider, say, a static potential, and then so conventional wisdom will tell you the static potential that's just all it is. It will sit there and it's static and it won't do anything. But like we were pointing out before, Whittaker's decomposition is that he pointed out that no, you can actually get a set of what he called bidirectional waves, that you can sit there and you can construct this static potential out of two opposing flows. Very much like what we have with the symmetrical gauging situation where there are two opposing forces. Conventional wisdom will tell you to sum that to zero and there's nothing there. It's locked up, you can't do it. So with a scalar potential, we have the same thing that, as Whittaker showed, where you have two opposing potentials. So to all intents and purposes, you can kind of get away with the static notion, and you can't do much with it. But of course, when we're talking about making the situation asymmetrical, then you've got to take in these flows into account. So I guess you could talk about exactly the sort of processes that you might consider to actually change or make the system asymmetrical, so you can make use of those bidirectional flows.
Well, the first thing that we missed somewhere back along the line in the standard stuff that we get taught at university is that energy doesn't occur like ears of corn stacked in a corn crib. It occurs in sets of flows, because the static potential of Whittaker in 1903 showed that decomposes into bidirectional energy flows, a set of harmonic flows. So more fundamentally, it's a set of flows. But if I'm also considering that in terms of general relativity, I've said that a curved space-time is also a set of energy flows, or a set of, if you wish to call it that, a set of flows of curved space-time.
Sure.
And so from a curvature of space-time that you make one time, or from a change in the vacuum virtual particle flux that you make, what you do is you change the energy flow. You have a steady flow of energy coming out of your source, your dipolarity, your poles, your terminals, whatever, or your charge. And it is real energy flow. It's a real space-time curvature. When you intercept that energy, the space-time curvature changes. It's a real change in the vacuum virtual particle flux, because where you are catching it, the vacuum virtual particle flux does change. If you change the curved space-time that the vacuum is embedded in, it changes anyway, because the energy density changes, which means the virtual particle flux changes. And I like to get around these barriers between that. I like to think in terms of when we're modeling, the real model mathematicians tell us we only have to have one single fundamental unit, and we can make a valid physical theory that will describe all that we know about physics and everything just as good as the regular stuff, with only a single fundamental unit. Now, there's an actual physics used like that, at least one, maybe more, but at least one of them uses length, and Jackson discusses it in his third edition. Jackson also says there's been an awful lot of fuss and fury about this. It's a very simple thing. It's a modeling thing. But if you were to choose the joule as your single fundamental unit, then space and time both become functions of energy. Everything becomes a function of energy. Mass doesn't cause us any problem after relativity and Einstein. But before that, people couldn't comprehend that mass and energy could be the same thing. But actually, everything can be nothing but energy or a function of energy, space, time, and everything else. So now all of a sudden, if we say, I have a curvature of space-time, I've said I've had a change in energy function, and it's kind of not too hard to see that that can be since it decomposes into a set of flows, I've changed a set of energy flows. And the same thing in considering it from the vacuum viewpoint. The main thing is, once you have a gushing well, even if it's just a steady flow, the problem is now okay, given that I have an unending, forever available flow of energy, as long as I won't mess up the dipole, then how do I merely collect this energy and then use it? Well, obviously, at least one solution would be to have my dipole only able to radiate the circuit and potentialize those charges under certain conditions. You say connected to the circuit or you radiate it in a certain fashion. And only during a certain little time when the charges cannot move as the electron flow, as current, because then there's no power and there's no work. It's just a free flow of energy. Potential will flow forever from a dipole if that's all you ever require it to do. And then before I get ready to have current flowing in the circuit, I simply disconnect this source I haven't drained it at all. I haven't taken anything. The only thing I took was energy flow, and energy transfer is work-free. You can transfer all the energy you wish, and it pays to do no work. Well, else you couldn't just have energy flowing through space. It would cost you work to do it, and it doesn't. So energy transfer alone does not require work. You can pile this stuff up all you want, as much transfer as you wish. Doesn't take any work as long as you don't go back and hit this dipole. But then move your dipole, your source, and save it as a true external source that you haven't messed with. Now I've got a potentialized circuit, but now it's not complete. So I recomplete the circuit and allow it to, it's asymmetric because I just changed one potential. So it's got plenty of potential energy and it's asymmetric, so it's got a force, a net force, and it will dissipate that energy now through the load and give me some free energy and load till all of it's gone. Then do it again, and do it again, and do it again. And if it's coming out as discharge pulses, then what you do is you feed some of the standard electronic systems we built to take that and shape it into any kind of energy output you need. Sine waves, any kind of voltage, and so forth. So it's all doable if we realize that we must not allow ourselves to be limited by a single fixed model. Gödel already proved for us, and it's accepted throughout all science, no model is ever going to be perfect. He proved that very rigorously in 1930. And we know that the best model we can build is going to be other phenomenology than what we try to make it as wide and beautiful and all-filling as possible, but we know there's an outside to it doesn't describe. When we run into something that we must deal with or we wish to go deal with outside that model, we have to change the model to even look at it. That's the point we've missed. We've tended to go back into more or less dogma where we say this model is perfect. And if it isn't in this model, it doesn't exist. We should never do that from a scientific viewpoint. The final arbiter is the experiment.
Sure.
If I have this beautiful theory and I present one experiment which is replicable and doable and can be done that counters this, I have falsified that theory for that part of phenomenology. Now all this other stuff it described, we didn't falsify that. That's okay. Use it if you want to use it for that. But if you want to work out here, you can't use this model. You got to change your model. We simply haven't listened to Gödel strong enough in all our universities. And the thing is, this should be made very clear to the young student. Before you get a graduate degree, certainly, and certainly I think before you get a BS degree, I think you should have at least one seminar course, and say a set of 4 or 5 seminars, and you just have to attend to be there, to pass, in other words, but it's required. Where people go into models and what models are, and the ins and pros and cons of models, and the fact that you don't have to have that set of units that we've been teaching you.
Sure.
You can have all kinds of sets of units. You can still have a valid model. Now, it may be the devil and all to work in. We usually choose the units to make it more convenient to work.
Sure.
But if we really want to get at some basic things and we're willing to do the arduous work and use a computer and so forth, we could make it all energy, and then we could examine time as a function of energy. We could examine space as a function of energy, space-time as a function, all of it. And we haven't violated any physics at all. And anything we run into that gives us new insight, then we should see if we can't get a better model that we can, quaternions, for example, much better model. It's even higher group symmetry than tensors. Something like quaternions or so forth. Let's go have a better look at it. Let's get a better microscope to look at it and see if we can't describe that. Because once we have an engineering model that can describe taking this energy past the observable state, on over from the subquantal state, the virtual energy of the vacuum, the disordered energy, with a negative entropy operation. We already have the proof that we have that. Every charge does it. So now let's go use it. But we've got to change a model to be able to model it. Once we have a decent model fitted to enough phenomenology experiments, now we can design equipment. And with very little adjustment, it'll work. It'd be like building a radar. You've got to do some adjustment from the theory, but we know in advance we're going to pretty well have this radar working. And we can do the same thing here. We can design a system that'll do things we never heard of with the present models we have. And with very little tinkering with and adjustment, we can have systems that use energy from the vacuum. I really think that's the way we've got to go. If we ever want to get out into space, we've got to have anti-gravity. We can't carry all the fuel and everything with us. We're going to have to be able to take that from the space we're in if we want to stay there very long.
Sure.
So I think that everything we look at, if we want to do clean energy on Earth, we're going to have to take it from the vacuum, quit burning all the coal and fuel. Let's use that to do something better with it. But we're going to have the different model then if we do go after the vacuum energy. But if we do, we'll solve the energy crisis, never have another one again. We won't have dependence on foreign oil or natural gas either, or coal either. We'll have a lot less confrontations and conflicts and all between nations. We won't be poisoning the biosphere so much. We'll remove all of that. My goodness, we'll start reclaiming some of the species we're about to get destroyed from all these poisons and everything. But it really is a steady scientific process for doing it. And you mentioned the Whittaker work.
Sure.
That was very significant because in 1903 and 1904, as you know, Whittaker did this beautiful work where he took a scalar potential first in 1903. And he showed that mathematically it decomposes in this bidirectional flow. It really is a set of bidirectional energy flows. It's a much more fundamental approach than the overall field approach we use now with no internal structure. The field does have an internal structure, so does the potential from Whittaker 1903 and 1904. Now the beauty of that is it opens up, like in the medical field, all kinds of things we can do. We can change that structure. And let's talk with potentials now. When I radiate a body with a potential, it has potentials all in it. Those potentials superpose. The internal structure of the body's potentials on every cell, on every blood vessel, on everything, the heart, every organ, everything, superposes with this potential we put in. Now, if I put a very special set of potential operations in your dynamics, so that when this thing interacts with mass, it starts to produce that set of forces. Let's call that an engine.
Sure.
Before we have the forces, let's call it a precursor engine. It's in pure space-time. It's really sets of space-time curvature, or it's changes in dynamic changes and sets and patterns in the virtual particle flux of vacuum. Either way you want to look at it. But it's real. It just doesn't have any forces yet. But when the potentials merge and it passes over as a set bleeds over, diffuses into the other potential as part of its internal structure, it now begins to interact with the mass in the body, all the cells. What part would you like to interact with? Would you like to interact with the genetics? Would you like to cure a genetic disease? Every odd pattern in the body that deviates from normal has a certain engine of forces and all that cause that deviation and is maintaining it. If you can just as easily produce the opposites of all of those forces, and you can amplify it. And when you get it amplified, that's a reverse engine or an anti-engine for that disease. You can reverse that disease. That's what Priori showed. Nobody understood it, but that's exactly what he did in France. It's all is documented in the hard French literature. Cured cancer, terminal illnesses, all kinds of stuff. And they buried that work like it's never been. But it was real good scientists that worked with Priori. Potrezel was an eminent epidemiologist, world-renowned. The head of the biology section of the French Academy of Sciences worked with him. And it was rigorously demonstrated that you could reverse diseases. You wouldn't killing cells and all this, you could just physically reverse the pattern, the forces that had caused the deviation, and it would just change. The biologists would call this de-differentiation. It would change back to an earlier form. He cured cancer cells by turning them back into normal cells. And it opened up a whole new marvelous method of healing, which just got chopped down right then because we didn't have models or anything at all to describe what he was doing at all, or even understand it. Today we do. Today we do. And so we should go back and pick up that work, apply the models and all, and for God's sakes, let's go ahead and get much better healing. With an aging culture and civilization, more diseases of the aging and everything, and everybody playing around with biological warfare and stuff getting loose from them, we're going to need all the good changes we can get. And we could do it electrodynamically. All the chemistry is based on basically charge and charge dynamics. So if we can control the charge dynamics, we can control the whole biochemistry, including cell differentiation, redifferentiation, all the work we're trying to do now there. We could do that directly with the cell. Becker showed that. And very rigorously, he showed that you can take a cell. Specifically, he showed you can take a red blood cell. You can cause it to sugar its hemoglobin, turn back into an earlier cell. That's de-differentiation in biology terms. Then it redifferentiated forward, but not on that same line it had previously taken, into a new kind of cell that makes cartilage. It was curing bone, horrible bone fractures. Well, that wasn't what was necessary, and it was still a delta. It redifferentiated again, turned into the kind of cell that makes bone, deposit it, and heal the fracture. And it did it with simple potentials, and sometimes pulse potentials. But did it? He did, and that, by the way, is still used in many hospitals today, occasionally, for treatment of otherwise intractable bone fractures. And you can get healing with it that cannot be explained in any other fashion. But it still hadn't made mainline medicine, and it hadn't, the implications for a type of medical treatment that's based on real good physics and real good science has not been realized or followed up. Hopefully it will be. So everything we're talking about has tremendous implications in energy, has tremendous implications in medicine, transportation. My goodness, if you can do anti-gravity and unilateral thrust, you can really do communication. Wouldn't it be nice to get rid of all the diesel fumes and things like that, and the fumes from our gas vehicles? Still have your vehicle, but you got an electric motor in it, running very smoothly, and energy right out of the vacuum. No exhaust, no nothing like that. So at some point we're going to have to clean up the biosphere, or we're going to strangle in our own juice, so to speak. If you go to China today, China's had this explosive development, you know, of need for vehicles and things in their cities. And you go to the cities, it looks almost dark as twilight from all the smog and stuff in there, from all this stuff. Some of the most unhealthy cities in the world are in China today. And it's a human health problem. And it spreads, you know. Remember the dark brown clouds we got from Africa and so forth? So it spreads around the world. So sometime we're going to have to do that. We're going to have to do it with this stuff we're talking about right now. And to do that, we're going to have to go both at the internal structuring of electromagnetics, the engines. We're going to have to go at it when it's still space-time and still just pure virtual particle flux of vacuum, and then have that interact with mass. The beautiful thing is, since energy is free, if you just structure the energy in space-time form or in virtual particle flux of the vacuum form, all you're paying for is a switching and controlled energy. You can structure enormous energy for much less cost, like a heat pump. Maybe you get 10 times or 100 times the energy, in case of sweet, 1,500,000 times, of what you have to pay to put in. And then, but you can take the results of that and have that interact to produce very strong effects. And now you've got propulsion, you've got anti-gravity, you've got things like that when you can do that. Very useful things. Well, you know, several times during history they've reached the conclusion that physics was just about dead. Everything could be discovered was discovered.
Yeah.
The physicists themselves have reached that point.
Yeah, that was around 1901.
Somewhere back there.
There was a chap who used to, I was telling you about this guy, Balin, who he was a sort of string theorist, and he's an okay guy, but he's really very arrogant about, you know, how powerful strings is and stuff. And I heard this from somebody else, and this guy was sitting down. He's giving a lecture about string theory and stuff, and he sort of walked in and very promptly sat down and put his chalk up and says, "Welcome to the end of physics." And this was just so out of touch. Even the guys that were conventional guys, I could just walk up and smack him in the face then, you know, he was so out of line. But it's funny how many people will, because in strings there's a big, you know, as far as they're concerned, this is the ultimate theory, and you know, anything else doesn't even come close, kind of thing.
Yeah, and the funny thing is, as far as I know, they don't have a single experiment behind what they're doing.
It's so, to be honest, somebody calculated that if you were to do any kind of collision experiments to verify string theory, the ring would have to be the size of the solar system.
Oh, goodness.
That big,
Well,
so...
I guess we'll need a budget for that.
Exactly, yeah.
Hey, they've got a better racket going than hot fusion.
Everybody, increase taxes. You must submit to this experiment.
The way I look at it, though, I mean, the huge tragedy is that they tie up so many very, very good scientists working on something that has absolutely no practical
That's right.
That's their
benefit.
aim. That's
Yeah,
exactly what they want to do.
Yeah.
They want to park them doing string theory and everything else in the world you ever heard of.
Hot fusion, string theory.
And they particularly want to get different competing schools that argue like hell with each other.
Yeah.
The more argument, the better.
Do you know this is a fact? I mean, when you look at string theory, you know, in quantum field theory, you can have what they call off-shell interactions. Those ones are virtual. String theory cannot, under any circuit, it actually diverges. If you try to make it go off-shell, it becomes infinite. You can't do it.
Well, it's dead to begin. The source charge destroys that.
Yeah, sure. So, all of string theory is done both in on-shell stuff, which means it's all observable stuff. You can't do any virtual stuff with it. Not only that, the minute you start to make it
dynamical, like in field theory, it just becomes way too complicated. They just can't do it.
All the stuff they're doing is with static models. To this day.
Incredible, incredible.
Then they'll pick a guy like Brian Greene, and he gets all the good television gigs, you know, and he gets...
Yeah, sure.
They tout him around, you know, and he lectures here and he lectures there, and, you know, they got the poster boy for string theory, you know, Brian Greene.
Yeah.
You know,
That's not by accident. That's by design.
Yeah.
The other embarrassing fact is, of course, that, you know, with they're claiming, oh yeah, we can get the standard model physics, we can get all this exotic stuff. Well, the only way they can get the standard model physics is by fixing it. You've got a huge amount of redundancy, and they specifically have to choose the values to get what they want.
That's correct.
It doesesn't come out by design.
It's shaped.
Yeah,
choose your
sure.
coefficients is what it says. If the thing doesn't give you the right answer, change the coefficients.
And then they had the
Until it does.
and then they had the goal to say that, like, oh no, you like the standard model, we don't have all these free parameters, we have one free parameter and everything is fixed, so that tells us we're getting closer to the final theory. Well, you've just chosen about 20 others to fix your model. So
what about all this arbitrary stuff?
Yes, exactly.
Well, they do the same thing, you know, way back when they changed these two potentials. Everybody knew you had to change it where you didn't have an extra force, because if you did, you'd change the equations in the system.
Yeah, sure.
Nobody ever faced the issue that when I change the potential, I'm changing the potential energy of the system, and that's real energy I'm locking up.
Yeah.
Nobody ever said a word about it being, oh no, potentials are false, they're just mathematical figments. You had to wait till quantum mechanics before people started realizing the potential was even more fundamental than the field. Fields can be made from the potentials. And that it was the potentials that had the fundamental reality if you go down the quantum route.
Yeah.
So they just, and the thing with the ether, they never changed an equation. They just got up one day and said, okay, no ether, we're not using one. Big deal. And that was it. There was nothing else ever happened.
Yeah.
So it's everywhere we look, we had, you know, assumptions that just got locked in, and pretty soon they're knee-jerk reactions. Everybody just assumes it's true because it's always been taught that way.